Hello everyone, I'm Yang Liang, an application engineer from NOVOSENSE. Today, I will share with you the car seat ventilation solution from NOVOSENSE. As cabin gradually becomes smart, users pose increasingly higher requirements for cabin comfort. To this end, more actuators are used in the cabin to improve comfort. Seat ventilation is such a case. There are generally two types of seat ventilation, blowing type and suction type. The ventilation fan is typically hidden in the seat and transmits air through holes in the seat. Since the performance of the fan has direct effects on seat comfort, the fan is required to provide low vibration, low noise, good EMC, and reliable communication to achieve high-performance fan control. Two motor types are commonly used, namely brushed DC motor and brushless DC motor. Comparatively speaking, brushless DC motor can achieve real-time maximum torque output, while brushed DC motor can only achieve the maximum torque output in specific positions. Brushless DC motor provides a good controllability, which implies stable control of torque and speed. This also means that it has a lower vibration and acoustic noise. Due to the absence of commutator brush, the mechanical friction is lower, and the commutation spark will not occur. This also means that brushless DC motors have a longer service life and a lower electronic noise. Moreover, brushless DC motors can be precisely controlled, which implies higher efficiency to enable precise control of brushless DC motor. The approach of FOC, field-oriented control, is typically adopted. Current can create the magnetic field. Ideally, the current of a brushless DC motor is a three-phase current with a difference of 120 degrees between every two phases. To realize an easier design, the controller needs to undergo multiple transformations. First, through the Clark transformation, the three-phase DC current is transformed from a stationary three-phase system to a stationary two-phase system. Then, depending on the rotor position, Park transformation is used to transform the stationary two-phase system to a rotating two-phase system. At this point, the brushless DC motor's three-phase AC current is converted to DC current synchronized with the rotor. This makes it easier for us to design the controller. When it comes to high-performance motor control, we pursue to output the maximum torque at the full speed range and stably control as well as dynamic response to high acceleration. When the transformed current is synchronized with the rotor, its torque at this point is actually the output, which is the minimum utilization state. When the stator's magnetic field is perpendicular to the rotor, the maximum torque output is achieved. That's an expected performance for a controller. After the Clark transformation and the Park transformation, we get a DC current synchronized with the rotor. Using a controller, typically a PID controller, it can achieve that the current is controlled and kept perpendicular to the rotor. We transfer the obtained control output by inverse Park transformation to get the output of alpha and beta in a stationary reference frame. At last, the SVPWM control is used to get the three-phase voltage, which is finally output to the three-phase bridges, to ensure the maximum torque output. The seat ventilation solution from NOVOSENSE adopts single shunt current sensing to realize current reconstruction with integrated PGA. For brushless DC controller, we use a BEMF observer, which is insensitive for variation in resistance and inductance of the motor, and provides a reliable angle observation. Through the bus voltage compensation across a wide voltage range, stable control can be promised. The optimized floating point control algorithm enables efficient operation on 32 MHz Cortex M3. In addition, NSUC1610 has an integrated power MOS, which only requires some passive devices to control a 20-watt motor. In the design of the motor system, the FOC algorithm requires a large number of controllers. We provide a parameter calculator to quickly calculate the control parameters of each controller, which substantially reduces the debugging time for users. As you can see, this is the seat ventilation solution from NOVOSENSE. This is the demo board for NSUC1610, and this is a LIN control box, and this is the fan for seat ventilation. To enable the overall control, our upper computer sends LIN messages to control the motor rotating. I'm going to send a message to achieve the maximum motor speed. You will find that after the alignment, it will reach the maximum motor speed very fast. The system has a wide dynamic voltage range. For example, now I adjust the voltage to 8V, the motor can run stably. When the voltage is set at 15V, the motor can also run stably. In addition, for this application, we also have designed some error diagnosis functions. When an overvoltage occurs, the motor will automatically detect the overvoltage and stop rotating. 19.41V. The value of overvoltage is configurable. When the correct voltage is restored, the motor will run again. In response to different stall situation, we have designed some stall detection functions. For example, rigid stall can identify rigid stall quickly, and after 10 seconds of the identification, the motor will make reoperation attempts. The soft stall will also support reoperation attempts after 10 seconds of the corresponding identification. When the number of the attempts exceeds 5, the stall error will be reported to the upper computer via LIN.